So can both of you hear me well? 예, 감사합니다. Thank you. Okay, so let's get started. Okay. Okay, so we are almost at the end of the semester, and we're gonna cover only one more chapter of the textbook, which is about continuations. And actually, this chapter talk about two things. So, motivation. / overview. So this chapter talk about two things, which are, the first thing is continuations. And although it explains everything in terms of denotational semantics, but implicitly in the semantics, it talk about something called Cps transformation. And the other thing that this chapter talk about is, although the John Reynolds doesn't say this way, but he's really talking about something called defunctionalization. Again, he explained things in the denotational way, but this can be understood as a mechanism that can be applied to a programming, to a programs in a syntactic manner. So it turns out, I mean, in fact, what really happened is that this CPS transformation and this idea of defunctionalization, I mean, they are not always used in a compiler, but they are two important concepts. Or you can say two important program transformations. Used by compiler for functional languages. So I will mention a few things why people do it. I mean, I'm not sure whether we have a time to cover this idea of defunctionalization. I might talk about it a little bit, but I will talk quite a bit about this continuation and CPS transformation. And these are the things that's used by the compilers for functional languages. And the reason is, if you think about what compiler has to do, it has to map highly sophisticated programs in functional languages into very low-level instructions in a machine. Low-level instructions in a machine doesn't support functions. I mean, doesn't support high-order functions. And then it's very primitive. So these CPS transformations and defunctionalizations are the ones that take care of, in a sense, it converts all these high-order concepts into the low-level concepts. In particular, CPS transformation take care of evaluation order, and also it takes care of the need for stack. So once you do the CPS transformation, you don't really need to carry around the stack. And I did the defunctionalization, convert all the high-order functions into records so that you can implement the what's going on in a functional language using low-level instructions. Okay, so this is, in a sense, overview about this chapter. But here's some motivations about continuations. Or maybe you can say it's another general introductions about continuations. So what are they and why we care about them? So the idea of continuation is actually quite simple. Continuation, intuitively, it represents rest of computation. So here's an example about continuation. Suppose we are writing programs of the form 9 multiplied by 8 plus 3 times 4. Okay. Now imagine that we are in the middle of computing 3 times 4. So then from the perspective of 3 times 4, once I complete the multiplying 3 with 4, I have to do something else. And what something else needs to be done? Something else needs to be done is recorded by this program with a whole. Okay. So once I compute, multiply 3 by 4, I'm going to get 12. Then I have to plug in 12 here. And then add it with 8. And then the result has to be multiplied by 9. Okay. So this programs together with the sum whole represents what needs to be done after finishing this multiplication of 3 and 4. So this is a syntactic way to think about what syntactic representation of what I mean by continuation. It records continuations, I should say, for 3 times 4. Okay. It represents what needs to be done, what the computation that needs to be done after I finish the current computation step, which is multiplying 3 with 4 in this case. Okay. So it's closely related to the program with a whole, but more mathematically, if we studied about denotational semantics of programming languages. From the perspective of denotational semantics, continuation can also be understood as a mapping that takes value, which is what I'm going to produce for the program that I have at the moment. So continuation take a value. Continuation is often written as a kappa. It take a value and returns some answer. Okay. So it's a continuous function that take a value and returns some answer. So what this continuation is expecting is the output value that I have to produce in the current computation step, like number 12 in the example that I just showed you. And this kappa, really correspond to this program with a whole. So in this specific example, this A is going to be actually v star, the value, and so this was value together with just normal error, type error, or bottom. And then this kappa, for the specific example that I told you, it's expecting a value, integer. So for integer. And then what it does is that it add 8 to the integer and then multiply 9, and then it embed it to this result space. So that's and then because the kappa should work for any value of v, we have to do something so that the input is not necessarily v integer but something else. So the point I'm making is that this kappa is exactly, I just wrote kappa that correspond to this program with a whole that I described above. And so semantically, continuation can be understood as a mapping from value to some final answer. And in this chapter, we're gonna consider the continuation, semantic continuation that has of this form. So the answer type, the answer domain is going to be v star. Okay, so just to recap, intuitively, continuation means rest of the computations, and syntactically, it can be understood as a program with a whole. Semantically, it can be understood as a mapping from values to some answer. And in this specific case, we're going to consider v star as everything in v star as a possible answer. So this is a continuation. And why do we care about this? And there are multiple reasons that we care about continuations. The first, and actually there are multiple places where continuations are used. The first thing is that a continuation can be used as a programming style. Okay. So sometimes people call it continuation passing style programming. I heard in particular JavaScript programmer use this type of programming style quite often because this allows you to get around the limitations of the language. And so here are just some example about this how program actually look like if you write program in continuation passing style. In the continuation passing style, if we want to implement, say, plus operation, so it's often written as a CPS, it takes 2 arguments, but it also takes 1 extra argument called kappa continuation. Okay. And then what it does is that it adds those 2 numbers. So kappa represents the rest of the computation, and it adds 2 numbers and it multiply these 2, you apply this continuation to the result of this addition. Okay. So it does. So usually continuation is implicit in when you write programs, but in continuation passing style programming, people write this continuation explicitly. And so for multiplication, this is a bit silly example, but so they do something similar, kappa x times y. So if we write a program like this as a continuation passing style, it can be written in this way. We said we do the addition of number 8 so no, actually this is not quite right. So since if you write program in CPS, often the programs is written, it's what people call it inside out. So instead of writing program from A plus 3 times 4, we write programs from what needs to be computed next. What needs to be computed first is the 3 times 4. And then to the result, we're going to add number 8. So in the CPS style of programming, we write this what needs to be computed first as a first entity, the outermost entity. So we have a 3 and 4, we get multiplied. And then we have to write continuation. So the continuation is expecting some integer. And then this for the integers, what we do is that we do the addition. And then what we add is that we add the number 8, which is the argument of this addition. And then second argument is something we just computed. And the final answer is going to mean the final continuation is just going to be an identity. We just return the value. So if you compare CPS style programs with the non-CPS style programs, if you look at the syntactic form, we write programs that the 3 times 4 is very inside of the program, but this 3 times 4 is very outside of the program. So sometimes people call it this CPS style programs as inside out programs. Okay, so that's one places where this continuation is used. It's used as a programming style, and then other place it's used is denotational. It's a so-called control operator. So the word control operator sounds very fancy, but one easy way to think about these control operator is that they are generalized goto. And then examples that we're going to look at is something called core CC and something called the throw. But there are many variants about this control operator. They are, in a sense, like a goto. So we put core CC, put a very generalized mechanism to put a label. Throw behave very much like a goto statement. But by using these things, you can do a core CC and throw are much more powerful than the simple goto. So by using this core CC and throw, you can implement something like backtracking. And also some other mechanisms like a coroutine. And I heard that there are some strange kind of generalized iterator. So I think Python supports some form of coroutine. So it also supports generalized iterator and so on. So various ways of changing the control of executions can be done by using these control operator. And in fact, one can show that in some sense, so these courses, we haven't thought about it yet. Maybe some of you who took undergrad programming language course from KAIST, they might heard about core CC and throw before. But we didn't really talk about it, but they are very powerful programming language constructs. If we include it, in some sense, we can extend the expressive power of a programming language. Okay. So the third place where we see continuation is the denotational semantics. So in fact, we look at the continuation passing style semantics of imperative programs when we studied the language with input, output, and abort. Okay. But for functional languages, this thinking about continuation really it really makes things a bit more different, and then also help us to understand what's really going on in these languages in a more fine-grained way. And also denotational semantics allows us to allows us to see how we can incorporate these powerful control operators into the language without any problem. And I don't know how many of you are familiar with, some result from mathematics, and not just in the denotational semantics, but also in some sense in mathematics. You will see something like a continuations quite a lot. So in particular, people often talk about, the vector space V, and they are thinking about its so-called dual space. That is linear functions from V to real number, if it's a real valued vector space. And this type of things appears quite a lot in the so-called functional analysis. And this is also can be understood as a so-called linear continuation. So this idea of dualization, which is very common in mathematics, it is very closely related to the idea of using continuation. The final things that I want to mention is continuation is used as inside the compiler. Sorry about this compilation step. The reason people do this, so this compilation step does is that it takes any program, and then it produces a program in continuation passing style. In doing so, it makes a few things. The first, the original program, if I want to implement this original program, we need I don't know how many of you remember what you learned in the hardware work. So if you run programs in a hardware, often you need to use two types of memory. One memory is called heap, the other memory is called stack. And stack is needed because if you make a function call, you may return and then do something and make another function call and so on. So just to store with what you have at the moment, and when you make a function call, that you need something called a stack. And that's different from the stack data structure. And but if you do this continuation passing style transformation in the compiler, you don't need a stack anymore. And then it turns out this is extremely useful to implement a compiler for functional languages, as well as to support what I call the control operators like a call, CC, and throw. And then the second thing is that original program. This program is from the Lambda calculus. So it has a Lambda abstraction and application and so on. But after this compilation step, the transformed program no longer depends on whether we use normal order evaluation or ego evaluation. So we said normal order in the ego evaluation, if you have a CF function application, we evaluate both operator and operand before applying the function. Normal order, we only evaluate operator, not operand, and then we just apply the function application. So they are different, but after continuation passing style transformation, transformed program, whether we are using normal order or using ego eval doesn't matter because our programs are very special. Okay. So these are the things that happens, and then it turns out having these two things is extremely useful to design a compiler for functional languages. So not all the compiler for functional languages employ this continuation passing style transformation, but some compilers do use this continuation passing style transformation. Okay, so continuation, just to sum up, continuation represents the rest of the computation, and syntactically it can be understood the program with a whole. Semantically, it can be understood as semantically it can be understood as a mapping that expects a value and return a final answer. So just a continuous function from value to v star. In this case, we are taking v star as an answer, and continuation is used as a programming style, control operator, denotational semantics, and compilation step. So what we're gonna do in this chapter is we'll mainly look at denotational semantics and control operator. And then we will discuss a little bit about compilation step. Okay, so let me start with denotational semantics. Okay. Continuation. Denotational semantics. So there are two reasons that I want to do this. It's because it gives a very smooth path towards this idea of control operators. And also it will help you to understand the impact of introducing how we can think about things in terms of computation in terms of continuations. So here's a reminder about what we did before. We defined the semantics of a programming language, the eager functional language, using this double brackets. And then that was a mapping from expression to environments and v star to continuous function. And then the environments was nothing but the functions from variable to values. And then v star was defined to be value together with error, type error, lifted. And then we looked at the definition of V, and I said the space of V is isomorphic. It's V and psi. So isomorphic to the sum, but then the sum describes what kind of values we have. We have integer values, and then Boolean values, also function values, tuples, and alternative. Then integer was very simple. Integer value was just a set of integers. Boolean values was a set of booleans. Functions was just function from v to v star, continuous functions. And v tuple is union union of all n's with n. And then the alternative was a set of natural number together with v. Okay, so that was the semantic domain that we used, and then we give a interpretation of all the programs in the eager functional language based on our intuitive understanding about what they represent computationally, and also based on this specification of these spaces. Now, so that's what we did, but then we want to change this setup such a way that we want our, we want our semantics to take not just usual input, but also one additional input which represent continuation. Okay. So what we want to do, we want to add continuations as a new parameter to the semantics of the semantic interpretation. It turns out if we want to do so, we also have to add continuation as a new parameter to functions. So we want to change the semantics so that the semantics is not just taking what you've already written there, but also take continuation as an additional parameter. Although it's not very easy to explain to you, that also requires of making some similar kind of change on the definition of functions. So what should we do? So here's what we can do. The change is actually very simple. So the change is that we're going to add something called continuation. Now we are not adding anything, but we are going to define something called continuation, which is just a continuous map from V to V star. So here, as I said, you should understand V star as a space for final answers. And then we're going to add V star as an additional parameter. So how can we do it? So we change this so that our interpretation is not just taking environment, but also it takes continuation and return V star. So it takes environment, but it takes additional parameter for continuation and then return V star. So that's one change. Another change we want to make is we want to change this function space so that function take arguments as well as continuation, and then returns the final answer. So now let me make one comment, okay? So I use V star before the change and after the change, but they mean something different. So V star here, they are the space for the final answers. So, I mean, in the textbook, John chose to use the same V star, but in some other authors, they use some other space called A, okay? So sometimes people call it A because it represents the ultimate final answer that we can get when we run the continuation. But setting this final answer, space for the final answer to be equal to V star makes things much simpler. But my point is that the V star that I wrote here and another V star that you see, so V star here, and they mean something, intuitively they mean something different, okay? V star, the underlined with blue, they are just, they represent computations in the standards, the semantics that we discussed so far. V star underlined with yellow, they represent the final answer. This specific case, they are the same, but they don't always have to be the same, okay? So from this reading, what does that mean is when we interpret this expression in this new semantics. So now when we interpret expression in this new continuation semantics, I'm gonna write it like C. We're gonna take two parameter eta and another the continuation parameter kappa. So eta is in E environments, kappa is in continuation, which is a value continuation. And then the whole thing has to return V star. Then intuitively what it has to do is it has to run expression E, and once we get the final outcome of execution of E, we have to invoke this continuation kappa to get a final answer. Okay. So this continuation semantics is defined in the syntax-directed way, and I will give you a few cases and then ask you to complete the rest. So here's a one simple case. If we have a constant n, instead of n, let's write specific number 3. And eta and kappa. Then this what we have. The final out. The answer here is the result of running the expression 3 is 3. And then I said we have to invoke continuation kappa. So the outcome is kappa apply to 3, but we have to do this embedding iota integer 3. So here's a quick reminder about all these iota notation. Iota int is a mapping that embed element of v int to v, and iota, say fun, so v fun to v, and so on. So we have this iota for all the runtime types like integer, boolean, function, tuple, and alternative. Okay, so then a bit more tricky case. Is a function application. So E1, continuation semantics, we take eta and kappa. So we have to do something. So now if you in the another big feature about continuation semantics is that it's very explicit about which expression should be evaluated first. So if we have an E0 and E1, in this case, we are expecting to execute the E0 first and then E1. So that can be formalized like this. We execute E0 under environment eta, but we have to change the continuation. Once we finish the computation of the operator, we will get an operator. And then that operator will have to be used. I mean, we have to apply that operator to the outcome of running E1, okay? So we take an operator F that has to be with fun. And then the next things we want to do is we evaluate its arguments in the continuation semantics. And then the outcome of this evaluating the arguments is going to be value. And then we apply this continuation kappa to the no. This is not done. So now we apply this function f to the value v, but now you see that the space of function is changed. It expects value as well as a continuation. So we plug in the given continuation here. Okay. So we first evaluate E0 under this new continuation, and then this new continuation is expecting function arguments. And once function argument is given, it evaluates its operand E1, and then once the outcome of the result of operand E1 is computed, is bound to V, then that's the time we will do the function application. Okay, so to be more precise, we have to put something called fun here. What this does is that if we have some operator G that goes from V theta to V star, we want to have this define G theta. It's a continuous function that goes from V to V star in the way that we talked about before. So G theta, if it's get a value V, it does the case analysis. If V is a value of type theta, in that case, we just apply G. So it's a type testing and type casting. Otherwise, it does raise the type error. So it's a one type error. This is when I talk about denotational semantics, I said this is the same as TYERR. Okay. So here I'm using this type testing and type casting operator because continuation should come with any values, but here I'm defining a function that is expecting only functions. Okay. So this is a general style. Intuitively, what it has to do is it computes the things that we have, and then once we get a final outcome like number 3, we invoke the continuation. So here's an exercise I want you to do. It may be a bit hard, but try it, and that's maybe the best way to understand this continuation semantics. Try to give an interpretation for variable x, and lambda abstraction, and also addition, and a few more, the tuple, pair, eta kappa, or continuation, and then the projections, E dot K. So let me be a bit more specific. E dot say 0. Let's say number 1. So first projection, C eta K. Okay, so I will give you 5 minutes. So try to complete these definitions based on what you see on the screen. Let's do 2 more because they will give you a complete picture about what's going on. Boolean and if then else. Not B. Okay, so let me give you answers to these questions. So the idea is, I mean, most of the time, if you just follow your intuition about what this semantics has to do, which is do the user computation and then apply continuation to the outcome of the user computation. So that's the intuitions. To the user thing, one additional thing you have to do is to invoke continuation kappa, okay? Because that's expecting the answer of the result of the user computation. So if you do so, here the user computation is gonna look up the value of variable x. But we have to, so this will return a value, and we have to provide this value to the continuation. So we invoke kappa here. That's the first case. The second case, we already given answer. The answer here is the functions. That's what we are defining here. So we, to the continuation, we provide an answer which is a lambda. That's going to be a function here. So we're gonna invoke this iota fun to embed the function that we are defining right now to the space of values. And how we're gonna define function? The function should be an elements in here. So it should take value arguments, continuation argument, and then return a final answer. So it takes a value argument, and then it also takes domain explicit. Take a value arguments, and then it takes new continuation, which is a frequent. And then once we are given v and kappa prime, then we run the body of this function, where use the same environments, but now variable x is going to be bound to v. And then the continuation that we're going to use is kappa prime. Okay. So one thing I want you to notice is here we are using, I mean, there are two continuations are available. So the one continuation is kappa that's given in the beginning. The other continuation is kappa prime that we are given when in the definition of this function that is here. Okay. So then the question becomes, which one should we call? Okay. And the answer here is that we should call this kappa prime. That is because this kappa prime represents the rest of the computation at the point of invoking this function. Kappa represents the rest of the computation at the point of defining this function. So kappa is related to the definition of the function, it's continuation at the definition of or declaration of this function. Kappa prime is the continuation at the invocation of the function. So when we invoke this function, we have to use the continuation that is available, that is, continuation at the invocation point, not the definition point. So if instead of using kappa prime, if you use kappa, something extremely strange is going to happen. Whenever you make a function call, you go back to the point of this function definition and do some strange computation. Okay. So two continuations are available, one at the point of definition, the other point at the point of invocation, and we have to use continuation at the invocation. Yeah. Now, what about the next? The next one is we said that we first compute E1 under eta, but then once the value of E1 is computed, we are expecting that should be integer. And then we compute E2 under eta. And if its value gets computed, 2, so free integer, Then what we're gonna do is we will invoke continuation kappa with addition of n1 and n2. So we embed n1 and n2 to the values, and then invoke continuation kappa. But because the continuation for an E2 is expecting integers, we have to do type testing and type casting. Continuation for E1 also expecting integers, we have to do type testing and type casting here. Okay. But note that we are very explicit about which expression to be evaluated first. We said E1 should be evaluated first, and then E2, so that this continuation passing style, continuation-based semantics is very explicit about evaluation order. And then for this tuple, we do something similar. So we interpret E1, and then we take value, which is the result. We define the continuation. The continuation take the value we want. That is the result of evaluating E1. And then we evaluate E2 on the eta. And that give another value, which is the result of evaluating E2. And then we invoke continuation kappa with the tuple formed by V1 and V2. So V1, V2, we form a tuple, and then we embed this tuple using iota. Okay. So the semantics is like this. I think let's not do the Boolean. I mean, there's not much things this adds. So the more cases appears in my lecture note as well as in the textbook. So have a look at them together. Complete definition about all the semantic, description of all these semantic clauses. Okay. So here we are evaluating E on the eta. Then the continuation takes value, but we are expecting tuple here. Then we did some check if number 1 is in the domain of the tuple. So if that's the case, then we invoke continuation with the first, this is actually the second component of V. Otherwise, there's a type error. So we just return a type error. And because it's expecting only tuple, we have to do type testing and type casting. So, right. So there's one other thing that I want to mention here. This type error, this is something that you saw before when we defined the semantics of this destructor for tuples, like a projection operator. But this is a bit different because when we talk about 1 comma type error here, we are talking about the final answer that considers not just the evaluation of this projection operator, but all the rest, which is encoded by kappa. Okay, so the previous so you can see that we are not just talking about evaluating this projection thing, but also the rest of the computation specified with kappa. So this 1 comma type error here means that the ultimate outcome, including the computation of kappa, has to be 1 comma type error instead of right. So that's the final outcome here. So good thing about having continuation kappa is we don't really need to make sure kappa propagates 1 comma type error to 1 comma type error. Instead, we can directly return the final answer at this point. Okay. Right. So this is the continuation passing style semantics. Does anybody have any questions? So I'm sure you maybe looks like it looks okay, perhaps, but then really, if you ask yourself, did I really understood what's really going? Did I really understand what's going on? Maybe the answer is not yet, or it's still a bit unclear. So I think the continuations, you have to play with it a little bit to get used to what's really going on. So now the other thing that I want to talk about is for CPS transformation. So before talking about this, let me mention this. So this continuation semantics and the usual semantics that we defined before has some relationship. Okay. Continuation semantics C and direct semantics. So the relationship is like this. So if we say, we take any expression and interpret in the continuation semantics under eta continuation kappa, and that gives the same result as kappa star of expression in under. So the left-hand side of this equality is a continuation semantics. Right-hand side of this double bracket here is for the direct semantics. So I said continuation semantics is nothing but direct semantics, direct semantics followed by application of the continuation. But this is defined in a composition of a syntax directed way. So proving this is not very easy, but there is some formal relationship between the two. And this is the relationship that's what we are expecting actually. Now let's get the other one. So we talk about semantics, but actually, this semantics directly tells us how we can do so-called CPS transformation. Which is the step that I mentioned. It's a program transformation, which is often used by some compiler. That's because it simplifies programs. Now, this how the CPS transformation works. So CPS, this is an operator that takes expression and it takes the expression and then it takes one variable that represents continuation. Check. And then it returns an expression. Okay. So it's a very syntactic transformation, but it satisfies the following. I mean, this is not exactly true because of error checking, but in the absence of error, this CPS transformation satisfies the following property. If you so if we interpret expression E under continuation semantics, and then under eta and kappa, and if we do the CPS of E and some fresh variable V count on the direct semantics with E, eta, where this continuation variable is bound to this is hyphen kappa. These two guys has to be the same. Okay. In other words, the what's going on in the continuation semantics should correspond to what's really going on in the direct semantics modular this program transformation done by this CPS. Okay. So this is the guiding equation about this transformation. And once you do this transformation, programs become substantially simpler in the sense of evaluation order and the use of stack storage. So how should we define this? So CPS is defined the syntax directed way. And then the equation that I just wrote here, this is the guiding principle. So if you follow this guiding principle, you can define the CPS for most of the cases. So let's think about the first one, which is constant 3 together with we count. So what should we do? In this case, I mean, we have to simulate the semantics, the continuation passing style semantics as a program transformation. And then in the continuation passing style semantics, we are given extra thing which is called continuation kappa. In the CPS transformation, we are given some extra variable we const that represent this continuation. So we do something very, very similar to what's going on in the semantics in the syntactic way. Here, what we do is that we just apply we const to value 3. Okay. And that exactly corresponds. Although there are some type testing, type conversion, and so on, this one looks, if you look at this, it's very, very similar to what's going on in the syntactic case. Okay? And so the CPS is defined in very similar way as the denotational semantics, the continuation-based semantics. So here's CPS for variable x. So I'll ask you to do some simple case, and I will do some more complicated case. So then yes. Also yes. Tuple. Okay, so how to define this? So let me give you a definition for here, for this case. And so here we do the CPS. We recursively invoke this program transformation. So we apply CPS transformation to E0, but we change our continuation parameter. So the continuation, actually, I was not quite right. This is not variable. It's an expression. So I think this one. Expressions. So what we do that we apply CPS and then we change the continuation. What continuation does is that it's a function that takes f, which is going to be correspond to the operator E0. And then we do CPS. For E1, that's going to give us the, so that's going, so if you, when you do the CPS of E1, that will give a value X, the operand X, So then we apply f to x, and then we because now our functions is expecting not just a single x, but a continuation e. So we have to apply e here as well, the given continuation from the outside. And that's very similar to what we defined here, but it's defined in a syntactic way. So this CPS is invoked. So the way you look at the description here is we invoke CPS transformation on E1 with this extra argument here that will produce some syntactic terms. And we form the continuations from there, from this outcome, and apply CPS transformation on E0. So maybe I will give you 2 minutes so to think about, to define the missing cases here. So actually, sorry about this. Let me write this like this. I think this may be the best way to express. More precise one is functional canonical form. Okay, so let me show you the rest. So the CPS of variable is also quite simple. So z is applied to x. You can see that that's very similar to what's going on in the semantics. It's a program transformation, but that mirrors what's happening in the continuation semantics. The lambda case goes like this. We apply something to yes, we apply something to the given continuation z, but what we're gonna get here is that we have a function that takes variable x, and then it takes continuation parameter f, and then we have to apply CPS transformation on the body of the loop, in the body of the function. The function is e, and the continuation parameter we are providing is something that's bound to this parameter. Okay? And that's very similar to the continuation semantics of the lambda abstraction. This case is also quite simple. CPS of E1 and E1, and then that we get a value V1, and we also call CPS of E2. We get the second value, and we invoke Z with a tuple V1 and V2. And the last case is we do the CPS of E, and we get a value V, and then we just take its first component, the second component, and then provide it to the given continuation Z. So that's the continuation passing style transformation. And you can see that if we get rid of type testing, like in the subscript tuple, or type testing and typecasting, and also other kind of embeddings like iota tuples and so on. these two semantics are, the semantics and then there's a syntactic transformation are very, very similar. And you can show if the error doesn't happen, the equality that I just described there is going to be true. Okay, so before finishing, let me mention a few things. So for this transformation, if you apply, so let's actually apply this transformation to something to see what happens. So suppose we are have a CPS, lambda x and 3 plus x, okay, and given parameter z. I mean, it's not going to be simple, but let's just do this to see how the whole thing works. Then we do that. We invoke z with parameter lambda x, lambda f, and CPS 3 plus x with f. We are not finished yet because there is some remaining transformation we have to do. And then that transformation said the f. We have a plus operation. So in the case of a plus, let's say the CPS 3. So maybe I didn't include the plus here. So plus is defined very similar way as the one above there. So we get a variable x1, and then we do the CPS x, and we get its binding x2, and we invoke continuation f with x1 plus x2. So, and then now if you look at, so here are the two CPS transformation we are not quite finished. So I'm gonna just write this, how this will actually look like. The CPS of the constant is defined by just invoking the continuation on 3. So here we have x1, CPS, and x2, x1 plus x2, apply to 3. And then CPS here is defined by something very, very similar. So we have lambda x2, f of x1, x2, and apply to the variable x. So if you plug in all these things together, you get the CPS transformation. Actual compiler does lots of optimization, but this is roughly the idea. Let me mention one more thing and then finish. The good thing about CPS transformation is that you can see some good thing about CPS transformation by looking at the outcome of CPS. Now, if you look at the function application, for instance, here. Function application, whenever we apply the function f, we always have a variables and then or canonical form. We said variable and canonical variables are always going to be bound to canonical form. In other words, variables will always going to be bound to values. So when we have a function application, operator f is a variable, so it's already fully evaluated. Operand x is fully evaluated. Z as a canonical form is also fully evaluated. So we can just directly go and then apply the function. So it doesn't really matter whether we are using eager evaluation or normal order evaluation. It's because whenever we are always applying the function to the values, okay? Well, canonical forms here. So that's one big benefit of this CPS transformation. And something similar here. So if you look at this projection, so it's arguing when you apply the projection, it's the tuple part, expression part is fully evaluated here. So by the time when you apply the destructor, we are only dealing with the values. So there is no ambiguity about evaluation order. Okay, so that's it for today, and we will continue and talk about through and core CC operator and a little bit about defunctionalization on Wednesday. Okay, so thank you very much.